Okay, so for the same power plant, determine how much energy is wasted. So that's QL. What's the heat sink, the what's lost here, and then assuming wasted energy heats up exhausted water. So let's say that lost energy goes into actually heating water. How many kilograms every second would water need to be sent through to that it doesn't heat up more than 5 degrees? So why don't you work through this one as well? Go ahead and pause the clip and see if you can do this one, and then you can check your answer when you're ready. All right, so for this one, we're looking for QL, and we end up getting, we have our output, we got that. So this is the loss. This is what's lost, right? So with that, that's what's lost and every second. And so we can look at MC delta T. This is the heat going into the exhausted water. We know the specific heat capacity. This can't go up more than 5 degrees, right? So therefore, we're looking for the mass that we would need to pump through there. And that's how much mass would need to be pumped through there with that energy going through. All right, so now we're going to take a look at wind turbines. All right, so when we calculate wind power, it's kind of neat to see how this works. We know kinetic energy is 1/2 mv squared. And what we can do is we can take a look at the mass per second of air going through the turbine. Now, you imagine the wind turbine there, you got your 3 here. So there's a certain area, pi r squared, that's passing through. So that's the area. Now, if you think about it, right, if you have something like this, you're going to have a column of air that's going to go back like this, right? And then it's going to close off. And then finish it back around there, right? So you're going to have a certain length. So if you multiply, let's say, certain length here, that would be the volume of air going through, right? But that's not everything that you have, right? So what you do is you multiply how fast, so the velocity, how many meters per second are going through, and we multiply that by the density, which is mass per unit volume. So the density of the air itself, and so put this in for mass, right? If we place this is mass per second of air going through. So in other words, we have pi r squared, which is the area. We have the density, the mass per volume that we have here, and then velocity, mass per, or meters per second, right? So if we multiply, it's meters per second, how fast it's going, that's length, which is meters per second. Then we have volume, so we essentially, this v pi r squared is volume per second, right? And then if we multiply volume times density, we get mass per second, right? So this is, if we place this inside here in for mass, this is what we get. We have 1/2 rho v area times velocity squared. And so this is how we calculate the wind power, per second. And so essentially wind power, right? Because we get how many joules per second that we get. And so if we look at the units here, our meters cubed cancel out, and we end up getting 1/2 mv squared over a second. So how much power that we get. So let's take a look at the situation. We have a wind turbine that has a blade length of 43 meters, and it receives air, a density of 1.1 kilogram meters cubed, and that's the air density. We have the speed of it is 22 meters per second. The effective power production is only 25%. So we want to figure out how much energy is produced in 15 minutes. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we should end up getting 3.402 times 10 to the 7th joules per second. and it's only 25% efficient, so this is the effective power. We know power is energy over time, so for 15 minutes, that's 900 seconds. And we know the effective power, so the effective energy would be 7.65 times 10 to the 9th joules. Okay, so we can go ahead and try this one, and you know, you can try part B as well, and this will be good practice. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so let's see how you did there. We should get for pi r squared, we have the area, and you know, we've got the velocity, we have the density, so this is the, you know, effective power here. It's only 35% efficient, so 0.35 times that number will give us how many joules per second. That's the effective power that we get. And our time is 2100 seconds, so the effective energy that we get there is 1.77 times 10 to the 9th joules. Now, the mass of air going through, right, is, you know, you take the density of the air times how fast it's going times pi r squared, and we end up getting how many kilograms per second that pass through. And so in the second one, you know, what's the specific energy of it going through? That's the mass that's going through, but, you know, if you think about the the total amount of time, that's probably going to be the easiest way to do this. That's the total amount of time, right? So every second it's this much, so we multiply that. That's the total amount of mass that we get. So if we take the total effective energy, which we got here, and we divide it by the total amount of mass, we'll get that. You could have done it for 1 second as well, and that would have been fine. And so, yeah, this one's a good practice to be able to see, you know, how these all interconnect here. Nice things about wind power, right? So the advantages, it's, you know, free, it's inexhaustible, you know, you're always going to have it, it's clean. Disadvantages, you know, it's dependent definitely on the local wind conditions. Aesthetically, it could be an issue, right? It could be an eyesore. Some people could consider an eyesore. And they are kind of noisy, and so I've heard of even folks that have had wind turbines close to them, you know, they can hear it going, you know, as it goes around. That could be kind of annoying. All right, so black body radiation is something that is important to consider. We know that, you know, objects are giving out thermal energy based on the emissivity, and so darker objects are closer to 1, brighter are closer to 0, and perfect black bodies radiate at 1. So let's consider the situation. Let's say someone's walking a dog at night. The dog's emissivity is 0.75. The temperature of the dog is 37 degrees Celsius, and the surface area of the dog is 0.45 meters squared. And we want to calculate the total loss of energy in 35 minutes when exposed to the temperature of 2 degrees. Now, when you do this, it's important to make sure that you convert both temperatures to Kelvin first. Then you take them to the 4th power. And so, you know, we have the 37 degrees Celsius plus 273 there, and then we have the 2 degrees. Now, it's interesting because if it's colder outside, then you're actually going to have a greater power output, greater thermal output. And that should make sense, right? Because the temperature difference is greater, we're going to have greater amount of heat going out, and that's what we get there. So when we get this, we should get 67.284 watts. Now, this is for 35 minutes, so we can convert our time to seconds, and our total amount of time be 141 to 96.4 joules. All right, so let's do this for a person. I'll have you work this one all the way through. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right, so we have our values in there. Should get 170.07 watts. That's being radiated out, and for 20 minutes, that's going to be 204,087.2 joules. So it's interesting as well with this, you know, the type of radiation, electromagnetic radiation sent out from an object is dependent upon temperature, and it's a good idea to use the sim if you missed class today to take a look at this black body spectrum simulation. I sort of showed it back in the heat unit, but it's important to be able to see this where, based on the temperature, you're going to shoot out different electromagnetic rays. And so, for instance, the Earth, us, we're at a temperature at which we're just shooting out, infrared, right? But we're not shooting out visible light. And so, that's because of our temperature. Now, what's nice about this as well is we can actually find the peak temperature, the peak wavelength shot out by a certain object. So for a human, for instance, if you used our temperature and we use Wayne's law here, we would find out that our wavelength that we shoot out is in the infrared spectrum. So what we're going to do is we're going to compare the average wavelength of Earth with the temperature of the Earth and figure out what the peak wavelength would be, and then also for the sun. And then we'll see, the peak of both of those. And so what we're going to do, the way this works is you find the wavelength here, that's lambda, by multiplying that by the temperature, and then you have this constant here, and this is on your equation sheet. So essentially you take this value, divide by the temperature, and you'll get the wavelength. And so let's do that for Earth here. If we look at Earth, we'll end up getting a wavelength of 1 × 10⁻⁵ meters as compared to the sun, which would give you 500 nanometers, which is close to, what about green? And so, yeah, so, that's the predominant color coming from the sun. We have predominantly visible light coming from the sun, whereas with, Earth and just normal objects, you just have the infrared. So here's a picture of it here. If you're in between the sun, close to the sun, peak wavelength for this, let's say this was a star, peak wavelength would be maybe around here. But for lower temperatures, you're going to have more infrared. And you also are having some ultraviolet here, beyond violet, right? So as soon as you get up to the sun, you're having visible light, ultraviolet, but you still have a decent amount of infrared here that's being produced. So when we talk about reflection and absorption, if we look at this picture, we know that, this blacktop here is going to absorb a lot, right? As compared to, the reflectors here, or, the lines on the road or the sidewalk, right, are not going to absorb as much. So when we talk about absorption and reflection, we can set up this ratio called albedo, where we have the total scatter power over the total incident power. And so a higher albedo means that there's greater